Hello students, welcome back. Previously in section 1a, we reviewed the definite integral, which we covered originally in Calculus 1. And a part of that is repeated here again as section 0. Now let's go to section 1, Riemann sum and Riemann integral. Let's begin with partition, which is defined like this. Given closed interval a to b, we define a partition xi as a sequence x0, x1, x2, x3, and so on, all the way over to xn, where the starting point of the interval a is x0, as I highlight in green, and the ending point xn is the end point of the interval b. Again, I highlighted in green. Now, the other n-1 numbers, x1, x2, x3, all the way over to n-1, all those fall in the interior, in the increasing order, strictly increasing order. You see, we have all those strict inequalities there. So these n-1 numbers in the interior divides the original interval in n pieces. First interval, subinterval x0 to x1, and then the next interval x1 to x2, and then x2 to x3, by far the largest, and then x3 to x4 in this particular case. Of course, you can put a lot more points in there, and then think of partition number as say 500. But then again, of course, it's going to be difficult to draw any picture and see what it's all about. So in this case, I took something really simple, n value equals to 4. Now, let's take care of some notations. The width of each subintervals are written as delta xi. Here, Greek letter delta means the difference. I hope everybody is already familiar with that notation from Calculus 1. Here's a reminder. Delta y over delta x, that is basically the difference of y coordinate over the difference of x coordinate. What is it? Rise over run, the slope of secant line, and that is approaching to dy over dx approaching to the derivative, slope of the tangent line. Remember this? Delta is the difference of y coordinate over the difference of x coordinate, so we get the difference quotient. And then we have something similar, but the difference is now infinitesimal. So infinitesimal over infinitesimal, so we have 0 over 0 type limit of this form, and that is the derivative. Remember this? You're using the same idea here. So delta means the difference. One more thing. In this picture, the third interval is by far the widest, and the maximum delta xi is named as delta x without the index. Why do we need this delta x? That's because we want to take the limit as the subintervals are all going down to 0. But then again, delta x1 to delta xn, there are too many to control all at once. But if I write delta x, the maximum, going down to 0, then everything goes down to 0 because even the maximum is going down to 0. So remember this notation. Delta x is the maximum difference. Finally, we say the partition Q is finer than partition P if Q includes P. So all the points in P are members of Q, as you can see from the first picture. Now, if you look at the second picture, partition R is not finer than partition P because P2 is not there. If you include P2 as well, then partition R becomes partition Q, as you can see. And now we get final partition. Okay, so much for partition and all the terminologies associated to it. Now let's go to Riemann sum. A Riemann sum is this quantity here, where yi is selected randomly between the minimum and maximum value of the function value in the subinterval, It's a little bit hard to see, so let's look at a picture. Let's see. All right, I got everything in the same viewing window. Here we go. So the Riemann sum is, this is a summation notation, summing up this quantity. So delta xi, which is the difference of x coordinates, so it's the width of the rectangle. Remember? Let's go to this partition again. Difference of x coordinate, so width of the subinterval. And that very subinterval is repeated here. And then the second, third, and the fourth. So delta xi is the width. And yi star is the height of this rectangle. You see, y1, y2, y3, and y4, there are 4 rectangles. And then the star, we are selecting anything in between. Here, the dotted line is a minimum, and the dotted line over there is a maximum. And then y1 star is selected pretty close to maximum in this case. Now, the second rectangle is a bit wild because of the discontinuity. Y2 star is selected between the minimum here and the maximum there. Anywhere in between at random. And then Y3 star and Y4 star. Now this program is randomized, so if I run it again, I'm going to get different pictures. Still different pictures. Anything in between the minimum and the maximum. Okay, that's the Riemann sum in general. One more comment before moving on to the next topic, and this may be a bit too advanced, so some students may not like it, but I would like to clarify this a little bit. Let's come back to this picture. The minimum here, well, there's a bit of a problem. What if the minimum doesn't exist? What if this is empty dot and solid dot is over there, so that the minimum doesn't exist? So this expression here is invalid for the second rectangle here. In that case, we can improve the second line by introducing the concepts of infimum and supremum in place of the minimum and the maximum. Should have been the infimum and the supremum, excuse me, in place of the minimum and the maximum for each subinterval. What is infimum and what is supremum? They work exactly like minimum and maximum, except that they always exist. Let's go back to this picture. What if this is empty dot, but I'd like to select this y-coordinate value? The minimum does not exist, but if you switch this minimum to infimum, then this quantity, infimum, always exists, so this expression is valid, and yi star can be selected anywhere in between. So improving this a little bit, we get this expression down here, and now we finally have the perfect definition of a Riemann sum. Sum of the areas of the rectangle, the width times the height. The width is obtained by the partition and subinterval width, and yi is selected at random between the infimum and supremum, which are exactly like between minimum and maximum, except that they always exist. So this expression is always valid. Now, if that's too advanced, it's okay. Let's come back to this. Now, still too complicated, so let's reduce it a little bit further and make it a little bit easier by restricting ourselves to continuous functions. Then what we do? We get down to this expression here. Why? For continuous functions, yi stars, which I highlighted in red, is equal to f of xi star for some xi star in this interval, in the subinterval. Why is the case is really hard question to answer. It's out of the scope. But it is related to something called the minimum maximum theorem for continuous functions. They always exist. And then in between is covered by OR, so intermediate value theorem. Both are very, very difficult, and they're going to be covered in real analysis 1, maybe real analysis 2. In any case, we successfully reduced this expression here into a single expression down here. And that works for continuous functions. And then the randomness of yi star is passed on to randomness of xi star in between, anything in between xi1 and xi minus 1 and xi. Let's see, do we have a visualization? Okay, here we go. So any yi star, y1 star, I can find x1 star so that the function value is y1 star. Here, I have two crossings, so I can always find x3 star here that corresponds to this y3 star. Yes, I could have selected the other one, but anything, you can select anything. And then this one crossing, so yeah. But look at the second rectangle. There's no correspondence. So this yi star equal to f of xi star works for continuous portion, but for discontinuous portion, it may fail. Sometimes I get lucky and I get crossing, but in general, I don't. Like this. As for continuous portions, I always have crossing. Okay, for continuous functions, I don't need to get y-coordinates and then this kind of restriction. I just have just one expression, sum of f of xi star times delta xi, where xi is selected anywhere in this subinterval. Okay, successful reduction by restricting ourselves to just continuous functions only, but still too difficult. So let's restrict even further to evenly spaced Riemann sums. That is, all the subintervals have the same width. So instead of taking partitions like this with all different width, take evenly spaced partition. In that case, delta xi's become constant. So width of the original interval divided by n. We still have some randomness because xi star is random. And that is the expression that our textbook shows. Let's see, do we have some time for visualization? Maybe one or two. Here's a visualization for arbitrary case for continuous function. As you can see, xi's are everywhere, so interval widths vary. And as you can see, consequently, we have some really fat rectangles, and consequently, the approximation of the area under this curve versus area of the rectangle is terrible around here and, in these places. Consequently, the function value, the Riemann sum value and the actual definite integral differ a lot. So this provides really terrible approximation. This program is randomized, so if I run it again, I get something different, something still different. And as you can see, you get wildly different pictures. Again, we have really fat rectangles and terrible approximation. Now, if I go over to evenly spaced partitions only, then we get something like this. Much better approximation, and then much less randomness. Widths do not change. Only the heights change. See the difference? Okay, let's stop here and let's resume our discussion in a separate video. Looks like we're going to need 2 more videos in section 1.